So happy Valentine's Day, my angels. Let's talk about what we've been looking at here. So we've been going cosmic is my phrase that I use to say that we're going into space. So when we go cosmic, when we go into space, first of all, for gravity, we can no longer use m little g, because little g is changing. Although we do, Matt, have a universal little g, gravitational field strength. We can calculate little g anywhere in the universe by going little g equals big G, big M over R squared. That formula is deliberately not on your yellow sheet. I've showed you where it's kind of hidden on your yellow sheet, and I'll remind you of that as we get closer to the test, which isn't going to be for a while yet. But then we also said, since little g is changing, when we're talking about energy, we can't use mgh, because little g is changing. And so we defined universal cosmic energy as negative big G, big M, little m over R. And we've just been playing with that for a few days. Why negative? We said out at the edge of the universe, since there's no gravity on you, you won't fall. And if you won't fall, that means you have no potential energy. So it's relative to zero at infinity. If you're closer than the edge of the universe, you would have to do work. You would have to add energy to reach zero. So you must be starting with a negative number so that when you add energy, you get to zero. Or it's also because it's an integral and it pops up when you take the integral when you do the calculus. So we've been playing around with escape velocity. We've been playing around with work. I think I told you example 3, I'm going to tell you right now, is going to be on your test, but I'm only going to be asking part VI. I'm going to tell you the mass of a satellite. I'm going to give you its orbital radius, and I'm going to say how much work to put it in orbit. And we'll do more of them as we progress. Some neat patterns. It says this. Use the expression for orbit speed, v equals the square root of big G, big M over R, to prove that once you're in orbit, that's a circle, prove that kinetic energy is half the magnitude of potential energy. What? How would I prove that? Well, kinetic energy hasn't changed. What is the equation for kinetic energy? So if you're in orbit, I guess it would be a half m v orbit squared. And we do have an expression for orbit speed. So why don't I plug that into there? Now, when I square a square root, what happens? So I get this. A half, I have a little m, a big G, a big M, and an R, not an R squared, but an R. So, you know what? Off to the right here, let's write our cosmic potential energy equation, which was negative big G, big M, little m over R. That one is on your formula sheet. And I want you to notice the expression that I got for kinetic energy once I'm in orbit and compare it to that. Ignore the negative. That's why I said magnitude. Isn't this big G, big M, little m over R, but half as big? You want to know how much kinetic energy you have in orbit? If you know the potential energy that you have in orbit, ditch the negative and divide by 2. That's how much kinetic energy you have in orbit. You do not need to memorize this. In fact, you don't even have to have this at your fingertips. This is one of those times when I say, oh, this is kind of nerdily cool. I like the mathematics. So we can say this is half of the absolute value of the potential energy. Because it should be a negative, but cool. Munir, what does the second thing want me to show? Total. You know what? That's going to be the potential energy in orbit and the kinetic energy in orbit. What's the potential energy in orbit? Are we in orbit? Are we cosmic? Can't use MGH. I'm going to have to use my cosmic one, which is going to be negative big G, big M, little m, over, and I guess the R that I will use would be the R orbit. What about kinetic energy? Now, Mitra is correct. Kinetic energy is always a half mv squared. But didn't we just derive a nicer expression for cosmic kinetic energy when you're in orbit? It's going to be plus a half big G, big M, little m over our orbit. Lena, what number is sitting in front of the G right there? It's invisible, but what number? Sorry? And I noticed that this has a G, this has a G, this has a big M, little m, R. These are actually like terms. This is the same mathematically as negative 1y plus 0.5y. It's just that instead of a y, I've got a big G, big M, little m over R. What is negative 1 something plus a half of something when you gather like terms? Kevin?
0.5.
Positive or negative?
Negative.
You know what? This is what I was trying to prove. This is going to be negative a half of big G, big M, little m over R orbit. Manir, can you read to me what number 2 wanted me to prove again?
The total orbit.
Stop. The total orbit energy is half of the potential energy. Didn't we just prove it? Yeah. Oh, okay. Again, do you need to memorize that, Kieran? No. But if that pops up as an answer when I'm doing my homework and I happen to notice, this is half as big as my previous answer, I think that's kind of cool. Lyndon, what's the third thing it wants me to prove?
Total orbit energy.
Show that total orbit energy is the opposite of the kinetic energy. What did we just find in part 2? What was our expression for total orbit energy?
Negative half big G, big M, little m over orbit radius.
What did we find in expression for kinetic energy? Positive 1/2 big G, big M, little m over orbit radius. Oh! They are opposites. And so, Sarah, I don't memorize that. Once in a while, when I'm crunching numbers on a question, if I happen to find the total energy in orbit and I notice it's the same number as I got for kinetic, except the kinetic is positive and my total is negative, but they are identical, I must have done this right. That's really all I use it for, as kind of a handy-dandy. I couldn't have fluked into that. But you can totally survive without that. Example 5. A rocket at rest on the surface of the Earth blasts off from rest and rises to a maximum altitude or height h. You know what? To a maximum distance from the center of the Earth, big R. Write equations to calculate the work done. What do they want me to calculate, Ange? So I can't use force times distance because the force is changing the further I get from the planet. So I'm going to have to use the longer version of work, which is the change in potential plus the change in kinetic. Can you read to me, Ange, the last sentence of the question?
Assuming the rocket begins and ends at rest.
So, what's that mean?
There's no kinetic energy.
No change in kinetic energy. And, no kinetic energy because they're both at rest. Is there a change in potential energy? What's change in anything? So this is going to end up becoming potential energy final minus potential energy initial. So obviously, don't write this down, don't write this down, don't write this down. Ange, why can't I go MGH final minus MGH initial? We're cosmic. Okay. So it's going to end up being final negative big G, big M, little m over, and I guess they want me to use a capital R for the final radius, minus negative big G, big M, little m over R, and I guess since we're starting off from the Earth, it would be the radius of the Earth, the 6.38 times 10 to the 6th, I think it is. I notice in the middle there is a minus minus, which is a... Now, because this number will be smaller than that number, this answer will be larger than this answer, which means you will always get a positive answer because you do have to do work to get into space. So this is why I said way back when I introduced cosmic potential energy, I said, look, the numbers, Lena, are going to look weird, but as long as you're careful with the signs, got you zoning out, as long as you're careful with the signs, very careful with the signs, you will get answers that make sense. Even though we've defined potential energy as negative because we've defined infinity out to be 0, it'll all take care of itself. Would this get you into orbit? No. Why is it impossible for you to be in orbit right now? Yeah. This is just how much fuel it takes on the weekend, and I wish I'd been paying attention. I should have played it on Wednesday during class. Last week, the Falcon rocket launched. Okay, how much orbit just to get, how much energy just to get it up there? That's what you've calculated, but that would come crashing back down if we didn't give it some kinetic energy. So this is how much work required to lift something into space. This will not keep it into orbit. Why not? Need KE, which is going to be a half mv orb squared. Give you a slightly different way to think about this. Similar situation, a rocket moving this time at speed v at liftoff. So now, instead of starting out on the ground, we're starting off right after it's left the pad. And just to make things easy, Matt, let's assume right when it left the launch pad, it's going at its maximum speed so that we don't have to have that, how long does it take to get to maximum? It makes the tough question tougher. It rises to a height h with no engine use. So it fires its engines to get up to speed, and then it coasts the rest of the way. Read an equation to calculate the maximum height using conservation of energy. Matt, is this question saying how much work? In fact, it's saying use which method? Conservation of? G. Yeah. Is there a change in height? Is there a change in speed? I think so, because we're starting out full. In fact, I think you're going to be slowing down. This is really the same physics as throwing something into the air, but now we're throwing something into outer space. We're going to ignore air resistance because that makes the math yucky. But, so is there a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky curvy force? That's a job for conservation of energy. G. So we're going to go like this. Kinetic initial plus potential initial equals kinetic final plus potential final. It does say I can assume the rocket ends at rest. So this is just firing something straight up, and then I guess it's going to fall down. Maybe it'll open a parachute and survive. Let's add that just so we don't have destruction and chaos everywhere. It's going to be a half mv initial squared, and that initial will be your launch speed, plus, Matt, why is this wrong? Okay. So what am I going to put here instead?
Negative big G, big M, and
Which are? Right? Initial, but, and I'll put Earth, but understand we could, any planet, if I gave you a different radius and a different planet, we could handle it. Equals negative big G, big M, little m over R. I'm not going to call it orbit because since it's ending at rest, it's going to come crashing down. So I'm just going to call it R final. What could we find with this then? As far as I'm concerned, there are three main variables. If you want to circle them, you can. There's that one. Well, actually, there's only two. There's that one. I would either tell you how fast we were going at the beginning and say, what's our final radius? And then from that, you could find the final height by subtracting our Earth. Or I would tell you how high we got. How fast did we have to launch? Okay. This one is a bit yucky. Here, where is the R? On the top or on the... I would not try and get this by itself. What I would do is I would crunch this as a number, get one answer, then I would times the R over, divide the answer over, and go from there. In other words, if I know how much kinetic energy we start with, we can calculate maximum height, or if I know the maximum height, I can figure out how much kinetic energy I need to start with. That's a nice test question. We can also have a rocket moving at a speed v at liftoff near the Earth's surface, but it barely escapes the Earth's gravity with no additional engine use. So now we're escaping the Earth's gravity. Write a conservation of energy equation that would allow us to solve for v. Note, we call this, what did we call this when you got away from Earth's gravity? What kind of velocity did we call this? Yeah, so we call this, I'm going to make up several versions of my test. On at least one of them, there's going to be an escape velocity written question. In fact, I think what I'm going to do, I'll even tell you, I think I'm going to calculate the escape velocity near a black hole. So we'll get massive answers, just to give you something different. Okay. Am I going to go work for this question? Ange, am I going to go change in potential plus change in kinetic? Say no. What does it want me to use? What it suggests I use here for escape velocity? Conservation. Okay, so it's going to be, again, kinetic initial plus potential initial equals kinetic final plus potential, why did I write final? Potential initial equals kinetic final plus potential final. Notice how this first line, I think, is the same line that Matt came up with earlier for the previous question. Now, which ones of these are 0? It does say that we end up at rest, so we can do that again. Out at infinity, that's 0. And so really what we have is this. Kinetic initial plus potential initial equals 0. Kinetic energy, Mitra, never changes. It's going to be a half mv initial squared plus. Can I use mgh here? Or are we going cosmic? Okay, so I have to use negative big G, big M, little m over R initial. And R initial, I guess, would be radius of the Earth. If it was a black hole question, how far we are from the center of the black hole. Equals what? 0. I would plus the negative term over now. And this is what we got for escape velocity. We ended up with a half mv initial squared equals positive big G, big M, little m over R final. We noticed the little m canceled, that the mass of the rocket was irrelevant. Am I wrong?
Is it
R initial.
F or I?
Thank you, Kevin. I don't know why I keep doing that. And so it seems to me I could either tell you the mass of the planet, the radius of the planet, and say, what's escape velocity? I could give you escape velocity and the radius and ask you to figure out the mass of the black hole. Could I not? In other words, there's 3 variables here, that one, and that one. And as far as I'm concerned, I can give you any 2 and find the third. And your Q would be the phrase escape velocity. Should be called escape speed because there's no direction, but we call it escape velocity, so I'll go with what they call it. D. I like D, I like D, I like D. Oh, I like C, I like C, I like... Oh, I like B, I like B, I like B. These are all ideas of how I can take this concept of cosmic potential energy, Sarah, and just muck around with it. What can we calculate or figure out or predict? So here, Sarah, what does D want me to find? How much what? So am I going to use conservation of energy? G. What does it want me to find? How much? So I'm not going to use kinetic initial plus potential initial. I'm going to use my work equation. And all of you underlined, here's the key. We are in orbit. So it's going to be work equals the change in potential plus the change in kinetic. And now I'm going to kind of split these up a little bit like that. What's changed in anything, Sarah, my joy? So this is going to end up being negative big G, big M, little m over R orb, that's the final, minus negative big G, big M, little m over R initial, which is going to be probably the Earth or whatever planet we start from. This is where, when we did this a couple of days ago, I started using ditto marks, and we just started repeating things on our calculator because we noticed everything on the top was identical except this one has a minus minus, so Sarah, it's going to be a. And I just would change the R. The change in kinetic, what's changing anything? Now, we said always assume we're launching from the Fortress of Solitude at Superman's North Pole. So the change in kinetic is just going to be kinetic energy final, which is going to be a half mv orb squared. I might give you the orbital speed. If not, we could calculate it. How would you calculate that? Gravity is what's pulling me in a circle. In fact, I think you would get what we had on the previous page. I'll come back. But I think you would get, this is what we got for orbital speed. It was big G, big M over R squared. This isn't meant to be a joke. This question is a lot of work. And I will ask you on every, this is one question that will be on your test. I'll give you an entire page. It's a lot of work. We can also look at asteroid impacts. In fact, I'm going to do an entire lesson on that next class. A satellite moving at speed v at a distance big R from the Earth's center falls to the Earth's surface. Caleb, what does this question want me to find?
How fast will it hit the Earth?
Did it say how much work?
No.
So Sarah, I'm not going to go change in potential plus change in kinetic. W equals that. What does it want me to find?
How fast?
Is there a change in height?
Yeah.
Is there a change in speed?
Yeah.
Is there a yucky curvy force? How would I handle this one? Nate, conservation of energy. So I'm going to start out going kinetic initial plus potential initial. Now in this case, initial is in outer space. Equals kinetic final and potential final. And in this case, final is on Earth. You have to be really careful with making sure you put the right things, Kevin, into the right place. Kinetic energy, Mitra, is what? Caleb, can I use MGH?
No.
Negative big G, big M, little m over R initial. And both of those would be how far you were starting out in outer space. Equals a half mv final squared plus negative big G, big M, little m, all over R final. R final would be the surface of the planet. Or I could even just say it falls halfway down to the Earth without hitting it. How fast is it moving now?
For PDF, since it's on Earth, couldn't you use gravity?
No, and the reason is, since we've gone cosmic here, great question. Kevin said, if PE final is on the Earth, can't we just use MGH? Because we've committed, we have to go cosmic here, we have to be consistent. We have now, by writing this, defined 0 to be out at infinity, but if you use MGH, 0 is on the Earth's surface, and now we're being inconsistent.
Okay.
This is probably the longest in terms of lots of letters. Oh, what do you notice here, by the way? The little m cancels. So the speed of an asteroid hitting the Earth doesn't depend on its mass. The damage it does certainly depends on its mass. As far as I'm concerned, there are 4 variables. That one, that one, that one, and that one. As far as I'm concerned, I can give you any 3. Find the 4th. I can tell you how fast it hit the ground. How high did it start out from? Here, this question wanted to figure out V final, how fast it will hit the Earth. This one is kind of, I don't know if I'd ever ask you for the radius of the planet, but if you knew how fast it was traveling, you could figure out where its final radius was, I guess. I would probably do that if we were still in outer space. It's fallen for a while. Now it's traveling this fast. How far did it fall? How high is it now? Is that okay? And you'll notice these are all just slightly tweaking our initial approach and just saying, okay, what else can we figure out? So now we're doing some asteroid impact. Is this my last one? Yeah. A satellite in orbit, that's always important because that means I can calculate a lot of stuff. Has a gravitational potential energy of that. Its orbital radius is that. Did they give me a radius or an altitude? They give me a radius. That works. No, that's good. Which is good because I'm on a planet now. It's not Earth, so I wouldn't even. If they'd give me the altitude, they would have had to give me the planetary radius. This is the orbital radius. Okay. What does A want me to find? Big M. Are we in orbit?
Yeah.
You know what? The first thing I'm going to try, gravity, is what's pulling me. And I'm going to use cosmic gravity because we're in orbit. Big G, big M, little m over r squared. By the way, the equation for force looks an awful lot like the equation for potential energy, and all I can say is don't get them mixed up. I went with v squared over r because part B mentioned speed. The little m cancels. One of the r's cancels. Do I know the speed? So this isn't going to work. I could get the big M by itself, but there's two things I don't know there. What else have they told me that I haven't used yet? Potential. Let's try that. Are we cosmic? So it's going to be negative big G. I'll make a little note here. Stuck. Because there's two unknowns. So let's go negative big G, big M, little m over R. That equals negative 6.55 times 10 to the 10th. I'm trying to find big M. Do I know big G? 6.67 times 10 to the negative 11. That never changes. Do I know little m, the mass of the satellite? Yeah? Do I know R? Oh, okay. I can find the mass of the planet now. How would I get the big M by itself? Times the R and then divide by the negative big G and little m? Does that seem right? So mass of the planet is going to be negative 6.55 times 10 to the 10th times R divided by negative big G little m. Okay. I got m's kicking around here, so I'm going to go m planet, or you could put m with a little p subscript, because my big m's and my little m's aren't looking that different right now because it's late in the afternoon and I'm getting tired. Negative 6.55 times 10 to the 10th. Orbit 8.85 times 10 to the 6th divided by negative 6.67 times 10 to the negative 11, little m, 965. This is definitely a job for a calculator. We're well beyond my I can do this in my head stage. Is it a negative divided by a negative? So? Are you positive? I'm going to not even bother typing in the negatives. I know they're going to cancel. 6.6555, Mr. Duick. Don't do that right away. Times 10 to the 10th. Times 8.85 times 10 to the 6th. Divided by, and I'll put the bottom in brackets, 6.67 negative 11 times 965. 965, Mr. Duick. Close off the bottom. When I reverse engineered this question, I started with 9 times 10 to the 24th and then tried to come up with numbers that would give me that. Is 10 to the 24th gut seem right for the mass of a planet-ish?
Yes.
Yeah, they'll be in the 10 to the 23rd, 24th, 25th. I mean, a black hole might be in the 10 to the 30, 10 to the 31. I'd be much more worried if I got something in the thousands or 10,000s, because, no, planets weigh a lot. Planets have a mass, a big mass that's a lot. So I'm going to write 9.01 times 10 to the 24th, but either in the margin or on my calculator, kilograms, I would store a more accurate version of that. I'm going to go 9.006, 9.00599. In case I have to use this, I think I will have to use this. So I'll make a little note here, 9.0059. Wow, that's a 9 right there. You know what? I think 9.006 is pretty good because of all those 9s times 10 to the 24th kilograms. Okay. Tristan, what's B want me to find? Is that an orbital speed? Oh. Gravity is what's pulling me. In fact, you know what? I have that written right here. What do they want me to find? How would I get the V by itself? Divide what over? Yeah, I got it almost by itself. Good. And don't get so carried away with calculations that you just think we always got to move stuff around. Sometimes nature is nice to us, right? So I think V orb is going to be square root of big G, big M over R. Let's do a quick double check. Lena, do I know big G? Yeah, because it's always 6.6. I saw you shake your head the other time. It's always 6.67 times 10 to the negative 11. I just found the mass of the planet, and I know R. Good to go. So square root of 6.67 times 10 to the negative 11. Those of you that have that big G built in as a constant in your calculator, I'm jealous of you right now. Mass of the planet, I'm going to write 9.006 times 10 to the 24th, but I'm going to use my answer button. And the radius was 8.85 times 10 to the 6th. Is that right?
Yeah.
And that seems about right for a planet. 10 to the 6th for the radius. Black holes can have radiuses of 10 to the 4th, 10 to the 3rd, or even 10 square. They can be as small as a couple of 100 kilometers across. That's why their gravitational fields are so dense when you're close to them. 6.67 negative 11 times, answer button, divided by 8.85, scientific notation, 6th, square root of that. Yeah, that seems right. 8,240. What's C want me to find, folks? Mitra, how do I find kinetic energy? What did I find in part B? V. Which M am I going to use here? Mass of the planet or the 965 mass of the satellite? Why? Because that's the thing that's moving. Okay. 0.5, 965. All right, 8240 squared, but I'm going to use my calculator. The nice thing is, once we've done the tough parts, the work does get a little easier. 0.5 times 965 times answer button squared. How much kinetic energy does it have? That much. Is that right? Works out actually kind of nice because I carried all my answers. So 3.275, 3.28 times 10 to the 10th joules. Kyle, what's D want me to find? Well, total is not a change in. Total just means add up what's there. And I guess up there we have potential and kinetic. What was the potential? I've scrolled down. Negative, what was it?
6.55 times 10.
And the kinetic I happen to have right here, 3.275 times 10 to the 10th. What do you get? And you should notice a little pattern. And this is what I said about 20 minutes ago. I don't memorize this pattern, but when it shows up, I smile and think I must have done that right. Did you get negative 3.275 times? In other words, did you just find out, are you ready? That the total energy was the same magnitude as the kinetic energy, but negative? Or it's half of the potential energy? Yes, it's exactly negative 3.275 if you actually add it up. Yeah? Really, Caleb?
Yeah.
Get off of it. We already saw the how to fly a spaceship to the space station video. I showed you that earlier. You folks are actually about a class and a half ahead of my other blocks because they've been hit by holidays and assemblies and all sorts of stuff. So stuff that you can try. Number one, change colors so it stands out a little bit more. It says write a work energy equation. What's B asking you to find? Is it asking you how much work? Don't write a work equation. Write an energy equation. I would use kinetic, conservation of energy, G. Number two. I would also use potential energy, conservation of energy here. Here, we reach infinity, except our final kinetic energy is not zero. We still have some extra. We're still moving. How much kinetic energy do we have at the launch? Okay. Please notice number 3 is from the moon. 3 is fair game. Four is fair game. I may come back to 5, but let me see. Oh, boy. I like number 8. I like number 8. I like number 8. Number 8 is a nice question. Except for number 8, I would just ask you part E. How much work to put into orbit? But it's walking you through all the things you need to figure out in order to figure out how much work to put into orbit. So right now I've skipped that. The total energy of the Earth orbiting the Sun. Man. 10 is good. 11. We've already done number 12. We found escape velocity from the Earth, and we already found an expression for escape velocity. We noticed, by the way, I think when I taught you escape velocity, I misspoke. I think I said, oh, it's twice as big as orbital speed. I should have said it's root 2 as big as orbital speed, because the 2 is inside a square root. Somebody on YouTube called me on that, and so I'll give that person anonymously a shout out, since they seem to be following my YouTube videos online if they're watching this one. I got your email, and I replied to your comment. You are correct. I made a mistake. So we'll cross out those two. Escape velocity from the moon is kind of cool. I skipped the next one. 16 is good. 18 and 19. I've thrown an awful lot, no pun intended, of work at you. There is no homework attached to lesson 5, the next lesson. In fact, we're really done everything new that I'm going to teach you. Next lesson, we're just going to practice a few more things and look at some cool, nerdy videos. Then we're also going to go over your circular motion test. Do I see you Friday? No? So I see you Monday. I'm thinking right now your test is probably going to be not this Monday, but the following Monday. It'll absolutely be before spring break. And I don't think it'll be the week of leading up to spring break. I think it'll be a bit before that. Is that all right? Rocket science. I would normally show you a cool nerdy video. I want to give you a good 20 or so, 15 minutes to tackle this. I have thrown an awful lot at you for a reason. I'm telling you right now, asking you to calculate how much work in orbit is going to be on your test. And so number 19 and number 18 and number 8, I'm also partly doing it just so you can get quick at the question and not get so bogged down that you don't finish the test.